In this segment, we're going to simulate our catheter design and see how it behaves given the left ventricular pressure. To do so, we're going to do this in Simulink. So we have the properties of the fluid, the density of the blood, the viscosity of the blood, and we're going to use just some test parameters here for our first design to the catheter length of 3 meters with a diameter of 5 millimeters at capacitance 3 times 10 to the negative fourth milliliters per millimeter of mercury. So we've already gone through, we made our circuit design model of this, and we can find out our transfer function. So what we're looking for is, given as our input the actual left ventricular pressure, we want to see what we're going to measure, since all we're in reality able to measure is what is the pressure across the capacitor or across that pressure sensor. And ideally, for this sensor, we want to measure as close as possible what the actual input is as our output. And we'll see in our first design that it doesn't do a great job at that, but we can refine our design to get a truer reading of what the actual pressure is. So if we go back to our just original design here, kind of picking these numbers out of thin air, I'll go into Matlab first. All right, so this file is already created, so I put in my value for the length of the tube, the diameter of the tube, the capacitance of the pressure sensor. I put everything here in base units, so meters for the length and the diameter. And the capacitance was given in milliliters per millimeter of mercury. I need to convert that to meters cubed per Pascal. So I just looked up the conversion rate here, and I have my capacitance in the correct unit so that it all agrees. The viscosity, the density, and we have for this circular catheter or this circular tube how we can compute our equivalent resistance and our equivalent inductance L. So if I just run what I have so far, and let Matlab do these calculations, I have my value of C and L and R. And if I go back to my transfer function, if I know L, C, R, and C, then I can convert from my input to my output. I'll take this now and I will run it in Simulink. So I'm going to start with the model that I've already made, but then I'll go through step by step how we can create this in Simulink. Right, so this is the one I already have. This is where we're going to end up. Let me make a new one so we can see step by step what these pieces are. So in this case, I'll take an actual left ventricular pressure. So I'll copy and paste this into our new model and see where this all comes from. So I'll just close these down. Right, so this is actual data that in reality we wouldn't know what the left ventricular pressure was, but this is the real pressure. And we want to compare this to what we're going to be reading across the pressure sensor or across this capacitor. So the first thing I can do is I can open up some model elements. And this is basically a wiring diagram that is going to run our simulation. So I can start by pulling in a scope. And I can drag and drop that into my circuit layout. And I can click and drag this wire into the scope. Now up here, this is how long I want to run my simulation. So this left ventricular pressure is going to repeat itself. I'll just do it right now for 6 seconds. And if I press this run button, it's going to run my simulation. So in this case, I'm just running the data into a scope. And if I double click my scope and I auto size it here, this is what my actual left ventricular pressure looks like. So let me double click this wire and give it a name of LV. I'll rerun this. Right, so this is what the real data looks like. This is the actual pressure inside the left ventricle. But in reality, we don't have access to this. That's why we're creating this catheter so we can measure this from outside the body. So what I want to do is go back into here. I'm going to take this signal and I'm going to put it through my transfer function, which represents it going through the catheter. So if I do a search in my library for transfer function, I want transfer function, not the discrete one, but this one up here. Right, so I can control click on this wire, and I can have this signal go into my transfer function. Now, transfer function again is this LC S squared plus RC plus 1. So I need to put the correct coefficients in for my denominator. So for the S squared term, it's L times C, which I can calculate in Matlab. I'll just copy and paste that. Put it in here. Then my second element is R times C, so I can calculate that in Matlab. And then the last coefficient is 1. So if I go back into my Simulink model, it's too much for it to display all at once, but it's going into this proper thing. So the left ventricular goes in, it'll go through the transfer function, and then what comes out is going to be P out. That's what I'm reading across the sensor. And I want to see what this is also. If I go in my scope, and I go here into its options, I can have it show multiple signals by changing the number of axes to 2. And I can put my P out into the scope as well. So now my scope is going to show the actual pressure and then my measured pressure. So I'll rerun this and go back into scope. I have to keep auto-sizing it. This is a downside of the scope that we'll address in a minute when we do this all through Matlab. I have my actual pressure, and I have my estimation, or really my reading of what that pressure is across the sensor. And we see that they're fairly different. The left ventricular pressure peaks around 180. This is in pascals, but we're measuring over 200. We're having this kind of double dip here at the top, and we're having this ringing down here. So using these parameters that, again, I kind of picked out of the air, I'm not getting great results. What I can do, though, is change the diameter of the catheter and the length of the catheter or tube as well. I'm going to, in this example, leave my pressure sensor alone. Let's just say it's an off-the-shelf piece, and I can't adjust that, but I can adjust the type of tube I'm using that goes to the pressure sensor. Then what I can do is, instead of going and changing these values every time, I can just put in variable form my values for L and C and R times C and 1. And I'll make it a little bit bigger so I can see what it's doing. All right, so that's my general transfer function in terms of variables, which Simulink will understand how to use. We go here. So I clear everything. I see my workspace is empty. If I were to run my simulation now, it's not going to know what to do because it doesn't know what L and C and R should be. But if I go and rerun this segment, now in my workspace I have L, R, and C. Now I can go into my Simulink, and now I can run it, and it pulls L, C, and R from the workspace of Matlab. And it's able to run it. I can see my scope. I can see my results. So as we saw, the scope is a little bit difficult to use, and I would rather work out of Matlab. So let me just pull the scope up here. I can go back into my browser. So instead of just plotting these results directly, I can have it export these results directly into Matlab. If I do a search on workspace, I want this one, to workspace. All right, so whatever this name is what's going to save my data to in Matlab. So right now I'm just calling it SimOut. That's the default, and that's okay. We're not going to worry about the rest. We'll just use all the defaults. So I have to tell it what to put into my Matlab workspace under the variable name SimOut. If we look at our workspace now, there's nothing called SimOut, and that'll change in a minute. I also want to drop in vector concatenate. If I do a search on that. Right, and we'll see what this does in a second. So I want to give it my original left ventricular pressure. So again, control click and put that wire in. I also want my P out going in. And then I want vector concatenate going out to sim out. So everything that goes into this concatenate is going to be saved as a column in sim out that we'll see in a second here. So, and in the same order. So the top one is going to be my first column. That's my actual left ventricular pressure. And the bottom one, that's going to be the second column. That is my P out from the transfer function. So again, looking at the workspace now, let me rerun this model. All right, so we see here, going back now into Matlab, that I have a new variable called SimOut. And if I look at what it is within Matlab, it's a struct. It contains time data, and it has this column called data as well. And look what else it made in my workspace, something called Tout, which is a bunch of timestamps. But let me go back to SimOut for the moment. If I do simout.data, we see it's a 753 by 2 vector. This contains the first column is my actual pressure, and the second column is the measured pressure, or the P out. Again, the more columns I have in this vector concatenate, then the more columns of data I'm going to have. So I can change the number of inputs if I were to have more things I wanted to track. So the beauty of this is I don't have to use the scope anymore because I have all the data that the scope was plotting directly in Matlab. So I can use the better Matlab functions to do the plotting. So let me go back into Matlab and copy and paste some code that I already made here. So first what I can do, adding it to here, I can run this sim command. And what this does is if I run this command in Matlab, it runs the Simulink file with this name, which is my file name, which is here, which I, again, already made. Let me close out this one. Right, so it's basically the same thing I just created. So it's going to run the file with this name, and sim is the same as if I were to push this run button in Simulink. So if I run this, it's going to rerun the Simulink file, and it's going to re-export the value of simout, which is what I'm interested in looking at. I can also copy and paste out some other things here. So I'll just copy and paste the rest of this in. So line by line, I'm going to save into a variable called data, that 2 columns from simout. So again, the first column being my actual left ventricular data, the right column being from the pressure sensor. I'm going to save into a variable called LVP, the first column of data, and PS for pressure sensor, the second column of data, and then I'm going to plot them against each other. So the timestamps of Tout with left ventricular, and the timestamps versus the pressure sensor. So let me run this whole thing, and we'll get a better view so we can compare the two sets of data. So here the black line is the actual data, the red is from my pressure sensor, and we can see more clearly kind of the disparity between the two values. Nice thing about working it completely through Matlab is now I have the freedom to go and change these parameters. So I have all these already. I kind of arbitrarily chose these as well. I'm going to reduce my length of the catheter to 2 meters. I'm going to reduce the diameter to 2 millimeters. And I'm going to leave the value of C alone. So working in Matlab is going to use these new parameters, calculate the new R and the new L. It's going to rerun the Simulink file, and it's going to replot the new results. So with this new L and this new D, let's see what it looks like. Okay, so we see here that our results have changed. The red from the sensor is closer to our actual, which was about 180. It's below 200, which is what it was in the previous design, over 200. We have less ringing down here. It's a little bit truer. So this design already is a little bit better than what we just saw in the previous one, but still doesn't quite capture the actual pressures in the heart as well as we would want to if we're going to be using this medical device to make any sort of diagnoses or interventions if the pressure is maybe too high in someone's heart. But again, we can easily change these. So depending on the type of tubes that are available, we could test different ones that would be appropriate. So let's just imagine there's a 3 millimeter diameter tube and rerun this. So we see the sensor does not really, it does a worse job in that case. Well, if I go and make it even smaller, if they sell a 1 millimeter diameter tube, sensor's not very good here. Let me change it back to 2. What if I use a shorter tube? Right, so we see a shorter tube. The results are kind of the same as for 2. And just one more combination here. What if we use a longer tube? We see with a longer tube, 5 meters, actually we're underestimating what the actual left ventricular pressure is. But it does get rid of some of that ringing. And we see that introduces a lag here. The peak of our actual pressure comes a little bit before the peak from our sensor. So we could keep changing these two values until we got a sensor that hopefully matches fairly closely what we get what we get from the left ventricle.